record on the computer, share the screen. Okay. Yeah, chapter 7 does hit a lot of stuff, but if at any point something reminds you of something you would like to see me definitely go back to, just let me know. Okay, and this is one of those, so I'll have to be really clear in the notes here for us and for the chapels who I think are needing to keep referring to the recordings as they go forward. So 7.3 is about simplifying complex fractions. And the way that I think of complex fractions, they are fractions that are made out of fractions or fractions containing fractions. So fractions within fractions, if you want to think of it that way. And we have done this, well, I say we, you and I separately in math have done this with numbers before, just like what we talked about really for a lot of earlier chapter 7. We've done all this before, adding and subtracting fractions. Nothing is new overall, except the fact that there's now like X's and Y's everywhere. And I wanted to point out, so big picture thing, and this is where it gets a little bit unfortunate that I have not gotten a chance to review this chapter. Let's see. Yeah. I am going to stick with what I was thinking about over the weekend. The book gives us 2 methods for doing this simplifying. Method 1 and method 2. Every book I've ever taught out of does this, and I know why they do it, and I sort of sympathize, but it also creates a lot of confusion. I think what we will be doing is method 1 because it is clunkier, but it ties in better to what you know already about fractions. Okay, so that's what I'm going to emphasize in this class, and partially just for time constraints and partially just to avoid confusion. I don't think we need to be learning multiple methods of doing the same thing unless we have to. Remember back with like substitution and elimination, we had to absolutely learn both of those. Method 1 and method 2, I'm going to say I'll leave that for future classes. Do you? Okay. Yeah, I see the shadow of the police car too. So method 2, this one is actually more efficient. And as you go higher into math, like in, no, I don't know, college level algebra, you'll see it more often. But at this level, algebra 2, it's possibly more confusing. So it's kind of like when we were learning factoring in chapter 6, there was a method called trial and error or guess and check that I showed you guys just once, I think, and then we went on from there. Now with method 1, method 2, I don't even think I'm going to show you method 2. We're just going to keep doing method 1 just to avoid too much going on at once. Okay, so a complex fraction, you might recall something like this from the distant past. That's a complex fraction. And this is one that's made up of pure numbers. There's no algebra involved. So we'll just work a couple of these examples with pure numbers. And once we get the hang of that, we'll bring in the X's and Y's and learn what they really want us to learn. But it's good to have a great solid foundation of what we've done in the past. Now, so the big fraction line here, which I've over exaggerated, you've got, this is like the numerator of that big fraction. And this is the denominator. And you'll notice that each one of them is a fraction in its own right. So that's where things get complex, like they say here. And what we do in cases like that is the invert and multiply thing, which we had, I think, briefly referred to a couple of weeks ago. You take the bottom fraction, turn it on its head, and it's always the bottom fraction that you do this to. And remembering that 14 over 9 over 14 over 9, that equals 1. Everything that I've gotten there in the parentheses in the pink equals 1. And so I'm still legal. I'm only multiplying this gigantic, ugly fraction by the number 1, but I've strategically picked the way I disguise my number 1 so that it will cancel out. Because when you multiply a fraction like 9/14 by its reciprocal, 14/9, it's going to cancel away. So if I can do this, okay, I'll help you in just a second. I'll turn the light on for you, okay? So you're going to do this, kind of gently cross that out so I don't make the notes completely illegible. And what that turns into is 2/3 on top multiplied by the 14/9 that we put to balance. And what's on the bottom is really just the number 1 now, because a fraction times its reciprocal is just the number 1. And when you have a number 1 down there, it's completely unnecessary to keep writing that. You can, so as we get farther into this, of course, we probably won't ever write that 1. You can just go to this point. And this fraction, if I look at it just for a second, I don't see anything that I can cancel. The 2 will not simplify into the 3 or the 9. The 14 won't simplify with the 3 or the 9. So I just multiply straight across and I get 28/27, and that's where I leave it. Okay, so what some people do, I'm going to say this is the same method, but quicker. If you see 2/3 divided by 9/14, you can immediately convert that to 2/3 times the reciprocal. Because dividing by a fraction is the same thing as multiplying by its reciprocal. So you can go ahead and convert it without having to show all the steps I showed here. And then we get 28/27, like that. So this is, let me just say another example. I can think of like 3 different types of problems we need to look at before we even get into X's and Y's. What if we had 2/3 divided by the number 4? So in this case, it's still a complex fraction, but it looks for a second like you only have one little tiny fraction inside of the bigger fraction. You only have 2/3 because 4 is a whole number. But this fits the same framework as what we just did, because 4 can be rephrased as 4/1. So 2/3 divided by 4 over the 1 is the same thing as 2/3 times 1 over 4. 1 over, I'll keep the color coding there just to, and in this case, and I'm using the more streamlined approach just because this is likely more familiar to what you've seen in the past. But if you need me to put in more steps, just stop me and I can always do that, because you know, with math, particularly algebra, there's always like 50 different ways of showing something. And really the advantage of any one method over another is just if it makes more sense to you. In this one, I see a little bit of canceling that I can demonstrate. Okay, so the 2 and the 4 can cancel to a 1/2. And then I get 1 over 6. So my pre-reduced fraction. So this, just to show you, this is still considered a complex fraction, even though at first glance, the 4 seemed to be a whole number. It really is a fraction in disguise. And then the last example, and then I have to go help Matthew with something real quick. Last example before we get into the algebra. What if I had 2/3? Yeah, I'm going to help you in a minute. Over 1 plus 9/14. Okay, so this is the last example that we need to look at to kind of set ourselves up. And then let me mute here, go help Matthew. I'll be right back. Okay. So with this example, which is probably the most important example to demonstrate what we're about to do with the X's and Y's, the first thing I'll do after I recopy this is just make everything into a fraction, because that will make my next step easier. So 6 is really 6 over 1. 1 is really 1 over 1. And now I've got 4 separate things. Okay, now this example here, this is what I was referring to when I said method 1 and method 2, and that's not actually my terminology. It's just the way most algebra books call these methods. Not very descriptive, method 1 and method 2. So this is going to be an example of method 1. So in a way, what you've got one math problem up here where you're adding two fractions, another math problem down below where you're adding fractions. So method 1 is going to ask you to treat this entire gigantic, messy, complex fraction problem as two separate problems. So you kind of divide and conquer. First, you're going to look at 2/3 plus 6. Then you're going to look at 1 plus 9/14. And temporarily, you're not going to pay any attention to the fact that they belong all together to one larger problem. So what this means is we have to think about when we're dealing with 2/3 plus 6/1, we have to think about common denominators, and we need a common denominator of 3. And then when we turn our attention to the problem on the bottom, 1 plus 9/14, we're going to have to think about yet another common denominator. That'll be 14. And so again, two completely separate problems. Okay, so let me rewrite this so I don't muddle up the notes. And this problem, thankfully, the way I threw it together out of the top of my head, coming up with putting together the common denominators is not going to be that complicated because I made everything else ones. So if I want 6/1 to have a denominator of 3, like the 2/3, I multiply a 3 down there, and I balance by multiplying a 3 up here. So I'm looking at an 18/3 in a minute. And then down below, another common denominator. This one is 14, so I have 14 and 14. So let me go ahead and make that clear. Three. Okay, be careful over there. Common denominator of 14, like that. Okay, so what this turns into, still treating it as two separate problems, is 2/3 plus 18/3. And on the bottom, 14/14 plus 9/14. And of course, if you wanted to, I'm kind of working these two problems simultaneously because neither one is all that complicated. But if they were complicated, you could completely focus on, say, the top problem and get it squared away and then worry about the bottom problem. So you've got plenty of options. So what we get, again, who knows where this is going to go because I made this up off the top of my head since the book didn't give enough examples. So 20/3 is what the top problem comes down to. And let's see, 14 plus 9, that's 23/14. So that's what I'm looking at. And at this point, I am right where I was at the beginning of an earlier example, say this example, where I just had two fractions stacked on top of each other. So that's where I am right now, and it's time to invert and multiply. So 20/3 divided by that bottom fraction is the same thing mathematically as 20/3 times the reciprocal of the bottom fraction. And at this point, I check to see if anything reduces. Nothing reduces, which is not surprising because, again, I was completely going off the top of my head. I know that on the bottom here, this is 69, and then up top, I don't know what that is. So 280 over 69. Okay, and then that's where we're going to stop. Let me scroll up just a little bit to show. Okay, any questions about that? If you can grasp that, you're probably going to be good for the rest of. Okay, you'll be fine. Any questions about that method? Okay, well, we can go on to the X's and the Y's then. So, okay, but remember you can't touch anything if you get up here, okay? No. You can take your penguin into the living room and play with it, but if you're up here, you can't touch your penguin, okay? Because he makes noise. Penguin's a loud penguin. Let me see. Where's a good place to dive in? Wow, okay. They don't give a lot of airtime to what I am calling method 1, but the good news is any problem in this section, whether they want us to do method 1 or method 2, any problem in this section can be done as method 1 because the two methods are just alternatives to each other. So the first fraction that they give us very nicely ties into the first example that I made up, where you just have one fraction over another fraction. So nothing weird, nobody's being added or subtracted. So here's where, if we want to temporarily revert to the long way, here's where you can flip the bottom fraction and actually show that you flipped it. And the reason that this works is because you're only multiplying. So here again, I'll enclose that in parentheses to kind of emphasize that's 1. It's ugly, but it's just 1. And likewise, this is also 1. When I cross out my 15Ks, when I cross out my 9s, that's 1. So what I get in the next step, doing this the long way, I don't need to erase anything right now. Maybe later. Times 9 over 15K over 1 is what I've got right now. And we talked about how that 1 is, unnecessary once you've gotten there. Okay, so the whole problem boils down to 5K over 36M times 9 over 15K. And because they actually put some thought into this instead of me just whipping it out off the top of my head, they're going to get some nice canceling for us. So the K's, there's 1 on top and 1 on the bottom, so they're gone completely. The 5 and the 15 can reduce to 1/3. And then the 9 and the 36, what's that going to be? 4. So my final result, after all of that crossing out, it looks like up top, I was left with just a 1. Everything's gone except 1s, 1 times 1 essentially. And on the bottom, this is takes a little bit more thinking. 4m times 3, that's going to be 12m. The letter or letters, the variables that are left, just tag along towards the end of whatever we're writing. But any numbers have to be multiplied. So we have 1 over 12m. Okay, careful. I'm going to move my arm and you're accidentally going to hit your head, okay? There, so we have 1 over 12m, and that's our final answer. Okay, so that's the basics. It's the same exact thing in terms of big picture to what we were doing with the numbers. It's just now they've tacked in some variables, essentially. All right, this, part B, it's still going to be one little fraction on top over one little fraction on the bottom. It's just that the fractions look a little bit weirder. They've put a subtraction problem as the denominator of a couple of fractions. if we want to, now that we've seen one example with variables, we can go ahead and just do this a bit more streamlined. So top fraction divided by 3 over x plus 4 is the same thing as top fraction times reciprocal of bottom fraction. So we just always rewrite the top. The top stays as it is. It's that bottom fraction that turns upside down. And it might be helpful, just so we don't fall into the trap of like some illegal canceling, I'm going to put some parentheses to protect my x plus 4, to protect my x minus 4. And then when it comes to canceling, it looks like absolutely nothing can cancel. So this is going to be kind of a weird answer, 8x over x plus 4. Matthew, if you want to bring some drawing over here, you can do that. I put your drawing in the living room. And for the moment, I'm going to keep this in the order that it just flows from the problem. And then in the last step, if we don't like the order that all of those pieces went together, we can rearrange it because everything's just being multiplied. So we have the freedom to change the order. Okay, so we've got something like that. That 3 usually would sit out front, just like the 8 sits out front. Nothing cancels. I think what they are trying to get us to do, what they're trying to trap us into doing, is maybe like, let me do this and then I'll erase it. Canceling this x with like that x, like ripping apart that subtraction problem, when really you can't legally do that. X minus 4 is considered to be one thing. Okay, so basically here all they're doing, as before, just practicing that invert and multiply technique that might have been a while since we've tackled with fractions, but it should be, you know, vaguely familiar to everybody. Okay, part C. This is where we finally start getting into the good stuff. So let me make sure I copy this correctly because there's like A's and B's all over the place. Okay, so this is where you have a math problem on top, math problem underneath. We're not going to invert and multiply anything until we've done the math. So on top, this is a problem, an addition problem with a common denominator that is completely separate from the common denominator down below. And common denominators, if it's been a while since we've set that up with letters, remember that we have here a to the first and a to the second, and we want our least common denominator to be able to basically cover both of them. And so you just take the larger power when you're comparing powers of a variable, because a to the first fits nicely inside a squared. A to the second fits inside of itself. So if we pick a to the second, we've covered both of them. They would individually like divide into a squared. Okay, so this is a separate, completely at the moment, separate. And separate's one of those words I always feel like I'm misspelling no matter how I write it, but I think that's correct. Very good. You drew a beautiful M. M for Matthew. Okay, and then this is same thing with the B's. You have a B to the first and a B to the second. B to the second is big enough to cover both of those. They could both divide into B to the second. So that's going to be our common denominator down here. So what you can do, and I'll just rewrite the problem. It looks like we get sort of lucky here. For each little miniature problem, one of the fractions involved in each little miniature problem already has the common denominator. So that is good news for us. It means a little bit less work. Okay, so on top, I need everybody to have a denominator of a squared. So I can just multiply that missing a here. Yeah, it's an a squared, yeah. Well, close. And then below, we need everybody to have a b squared. So the one denominator that doesn't have a b squared, we can just fix it. We can just multiply in a b like that. Okay, so the top problem is now 5a over a squared plus b over a squared. B over a squared has not changed a bit. It was already in the form we need it. And then underneath we have 5a over b squared, which was already where it needs to go. And then we have
your timer goes off, Mama.
A few more minutes.
A minute.
Well, I'm not sure exactly. All right, so here's what we're looking at. Now, the addition step in this problem might feel a little bit weird because it's not as nice as when we're playing with numbers. When I add my top two fractions together, the best I can do is this. Because 5a and b are not like terms, so they can't come together cleanly. They just have to kind of sit there over their common denominator of a squared. A big fraction line down to the other addition problem, same thing. In fact, same exact two quantities being added, this time over a b squared. Okay, so we've finally gotten to the stage where we have a fraction, a single fraction on top of another single fraction. And what we're going to do is our invert and multiply. So this is where we rewrite the top fraction, nothing changes, but we flip the bottom fraction. So the b squared goes on top. And I just, because I'm sort of obsessive about this, I'm going to put parentheses to protect my little addition problems there, just so that we're not tempted to try and cancel out half of an addition problem. Okay, and when we do that, hopefully it becomes clearer to see that it is the addition problems
A letter.
that we're going to cancel. Who are you going to send a letter?
Oh, I'm going to thank you so much.
Okay, so those cancel. Oh, okay, that's a good idea. So all we're left with is b squared over a squared. Our little addition problems, thankfully, there was one on top, one on the bottom. They matched each other. They're gone now. And that's all that's left. Okay, now let me pause there again. Any questions about what I did with any of that? Matthew says he doesn't have any questions.
No.
Do you have a question? The actual student.
I said the policeman was still out there working, I said.
Oh, okay. No, he says he was actually talking about the policeman, not the math problem. So, okay. Now in the book, what they do at this point is they shift gears and they go to method 2. So I am going to just re-emphasize here. We will not officially learn method 2, because again, I think it's much better to learn method 1 and get really good at it. What usually happens is students learn method 1 and method 2 back to back, even in college. And they're just, the methods are too similar and they start making their own, like method 3, like they make a hybrid of the two methods and it just becomes, oh, did I write? It becomes a mess. I wrote method 1 there. We did learn method 1, goodness. We will not learn method 2, but we can use method 1 on those problems. So we can continue to work the problems in the sections. Wow, it is pouring down rain.
Why?
Well, it's a rainy day.
You remember yesterday Dad told me I was going to rain yesterday?
I don't remember that.
We're all having to stop yesterday. So the Christmas one will be rainy.
Oh, yes, I do remember that.
What do you?
Okay, so I'm going to jump to practice 3 because practice 2, they just go over the exact same problem that practice 1 was. A couple of the same examples, they just decide to use method 2. Okay, you need to get on your chair, okay, so you don't fall, because I'm going to move my arm. If you hold on my arm, you fall off. Do you need me to flip your paper over for you? You can go get your colored pencils too. You don't have to just use that pen. Yeah. All right, now, I don't like what they do here, but I think we can handle it. Because we've had chapter 6, we've had the exponent rules. I don't like them jumping to us having to do that, but once we get past the exponent rules, I think this problem will actually be a really good problem.
This is a shark.
So this problem is
This
not,
a shark.
it looks at
Mama,
first
this
glance.
is a shark.
Okay, I'll be quiet. He's drawing sharks. This problem is, sorry, I'm supposed to have an alarm on my phone and I forgot to set it. This problem does not look like a complex fraction because they have chosen to disguise the fraction part of it or the complex part of it. From back at the beginning of chapter 6, we learned all of those exponent rules, and one of them tells us how to deal with negative powers. X to the negative 1 can be rewritten as 1 over x to the positive 1, for example.
Yeah.
X to the negative 2 can be rewritten as 1 over x to the positive 2. And same type of scenario all the way around. All of these little things that I've circled really are fractions. They just are fractions in disguise. The only thing that's not a fraction, making sure I didn't copy that down wrong, no, the x itself is just an x. Okay, so we've got something that looks like this, and the challenge before we even get to the algebra will just be in how we set this up. So I have a 3 right next to a 1 over x. So that very first expression is really 3 over x. I had a 1 over x squared I discovered right next to a 1 over y. That's going to turn into a 1 over x squared y. And then we've got a 1 over y squared on the bottom plus, looks like x over y. Okay, so this problem we had to kind of uncover the fact that this is a complex fraction problem because it didn't look at first glance like complex fractions at all because they chose to write everything with these negative powers for reasons that I'm not sure about, but it is a good skill to know how to do this. I just personally would have left that for maybe a few problems in the future. Yeah, that's kind of weird. Okay, anyway, so let's see what our common denominators.
A chocolate bag.
Really? Okay. So we're going to have some kind of common denominator up top, which I'll have to think about. And then we're going to have a completely separate, usually, sometimes they come out to be the same common denominator just by complete coincidence, but I don't think that's going to happen to us here. Okay, so our common denominator in the orange up top looks like it needs to involve x's and y's. So we have to ask ourselves, what's the highest power of x? What's the highest power of y? And then just put those together. So the highest power of x is x to the second, and the highest power of y by default, because it's the only power of y, is just y to the first. So we've got a common denominator of x squared y. Okay, and then down below, there are no x's. That's kind of nice. So we're just asking ourselves, what's the highest power of y? And it's y to the second. So that's our common denominator. And as I've been doing, just I don't want to make a mess if I can avoid it. So let me just come and before we start giving everybody their common denominators, let me just rewrite the problem. Okay, so there's the rewritten problem, and that's the point where I start asking myself, who's missing? What's missing in order to create common denominators? So it looks like x squared y right here, that's good to go. That is naturally, kind of a naturally occurring common denominator in the problem. This other one, okay, so I have an x to the first. I need one more x, and I need a y. And if I do that to the bottom, oh, careful, Matthew. I have to do that to the top. So x times y over x times y looks like all I need to do to fix that so that I've got the common denominator. And this is where I was talking about if you want to just stay with these top two fractions and not worry about what's going on underneath, this might be getting to the level of difficulty where that would be beneficial. So let me rewrite. I've got 3xy over x squared y, if I've done that correctly, plus the 1 over x squared y that I didn't have to fix, that was already where it needed to be. And then if you want to keep going even beyond that, like work this top little tiny math problem as far as you can take it.
Why did your phone go down?
Well, it must have been not balanced right. Okay, and then you've got this. So that's as far as we can get with the top couple of fractions. We've identified their common denominator. We've made sure both individual pieces have that common denominator. We've added them together, and we know that still we've got big fraction line, big fraction line. We have to do the same type of thing down below with the fractions that I had kind of coded in green up here. So those fractions need a y squared underneath. Only one of them has that y squared underneath, which means the other one, so let me go ahead and say this is good. The other one needs an extra y. Okay, so I've got that. And it looks like my kind of intermediate step here. Well, if you're slipping, maybe go put your little Uncle Kenny slippers on. You've got xy, y squared. And then finally, 1 plus xy over y squared. And as I've been doing, just out of an abundance of caution, if I see an addition or subtraction problem, I am going to enclose it in parentheses to protect it. Whatever is in there is sacred. Like you can't go and start ripping pieces apart. Oh, Matthew, I'm sorry. I don't remember where you put them. They could be anywhere. Let's see. So we've got one fraction on top. We've got one fraction underneath. And this is the part where top fraction divided by bottom is the same thing as top fraction times the reciprocal of the bottom. So I'm going to rewrite. X squared y. Hey, Matthew, why don't you check your bedroom and the bathroom? They might be in there. And then I'm multiplying by the reciprocal, or some people call it the inverted bottom fraction. And again, just so I don't fall into the temptation here, I'm going to protect this, protect that. And when I put those parentheses around, you can kind of see that the two little addition problems are similar, but they're not identical, so I can't just cross them out like that. A lot of times we get to do that, but this problem is not one of them. Good job. Okay, so I need to cancel what I can. Can't touch these addition problems, but it looks like I've got a y to the first and a y to the second. I could cancel what I can there. I can cancel y to the first here. And one of the two y's up top. So it's always hard to express this clearly without also making a mess. Let me just keep my color coding going so I change as little as possible. So the next step, I've got 3xy plus 1 times y to the first. It used to be y to the second. Now it's just y. Probably in the next step, I'll refer to it as just y. And then underneath, I have an x squared. But I don't have any y's at all because there was only one, and then I canceled it out. Okay, expression in parentheses here. 1 plus xy. So the final answer, if you want to, and this really is just purely subjective, like it's my opinion. If I have a y to the first, sometimes I like to pull it out to the front because I've got an x squared underneath. About 7 more minutes, your timer will go off, Matthew. Okay, so maybe this is my favorite way to leave this problem. Honestly, I could have left it a step back and that would have been fine. Okay. No, when the clock goes on 11, your timer will go off. Oh, just wait. Yeah. Looking at the homework section. Just wait, just be quiet for a few more minutes, okay? I'm going to pull some problems out of this homework section because they don't get anywhere near as detailed in the teaching part of all this as they needed to. I don't know why.
I forgot my picture.
Okay, if you know where it is, you can get it.
I do know where it is.
Okay, so something like that. Yeah. This is a good one for a couple of reasons. I'm kind of analyzing. First thing I'm going to do is this problem has 4 denominators. So I kind of ignore the numerators while I'm in this step. I look at the four denominators. Okay, you need to be quiet for a few more minutes, okay? And then your timer will go off. So there's four denominators that I need to look at to determine, okay, what's my common denominator up top? And then in a completely separate problem, what's my common denominator down below? And the trick to this, the reason that I enclosed, or one of the reasons that I enclosed those little subtraction problems in parentheses, is because I want to be able to correctly identify what pieces I have available to put together to make a common denominator. It looks like I have x to the firsts, and I have x minus 1s to the first up top. Those are my pieces that I can play with. And underneath, really, it's the same stuff. It looks like this is going to be a case where our entire problem ends up with like the same common denominator. So that happens occasionally. Okay, so I want to know what's my highest power of just x individually. And then I want to put that together with my highest power of x minus 1, because I protected x minus 1 in parentheses because I'm treating it as a single unit. So if there were any x minus 1s to the second or third, those higher powers would get copied into my common denominator. But here, it looks like just x to the first and x minus 1 to the first. There were no higher powers of either of those pieces. So my work is done. I don't have anything to compare and contrast. And then here I've got, same thing underneath. This would be a problem that I know they're really into making us do method 2, but I don't see the benefit to that. So let me rewrite this big messy thing. And I'm going to just keep that in parentheses. That'll help with what I have to do next. X plus 1 over x minus 1. Okay, so looking at the orange part of the problem, the part of the problem that is a little subtraction thing going on up top. We've only got 2 more minutes, just wait, okay? The first fraction has the x part that it needs, but it does not have the x minus 1 part. So I am going to put in x minus 1 on the bottom where I need it, and then balance by a corresponding x minus 1 up top. And as I do that, I see an x minus 1 next to an x plus 2. And another one of those unfortunate times where it's all on me to remember that that x plus 2 is a single unit, just like that x minus 1. And so I need to introduce the parentheses. The problem won't do it for me. A little bit easier down below, and there are so many options. The common denominator of x times x minus 1 is the same thing as x minus 1 times x. Like we've talked about a lot, multiplication doesn't care about the order. So if it's easier, you might, sometimes if you put things on the left, you run the risk of like the two fractions sort of blending together. So I'm going to put my x that I need here and here. I'm going to put it behind what was already there. I just personally feel like that might be a little bit cleaner. What that gives me is something like this. And then we know that after all of that work, finally, we've got our LCD. Matthew, alarm, do you want to come press the button? Come over here. I'm holding it down here for you so you don't have to trip. Here, over here. Well, let's try to help him now. He's gonna have to, yeah, don't trip. There you go. Okay, turn the alarm off. All right, so. Were you gonna do Frozen? Is that what you were gonna do?
Yes, I go find my answer.
Okay, well, we'll look for it next time. Okay. All right, too many things going on at once. Let me find his movie here. Okay, so down below, and I'm torn once again, like, is it more beneficial to work the whole problem at once? I think in this problem, just looking at lack of space here, I am going to try and bring this lower problem up to speed and switch to my green pen. Let's see. Okay, so the first fraction has an x underneath, and it really needs x and x minus 1, just like the last one. The two fractions have, again, those identical LCDs, identical common denominators. And let's see here, take that circle off. So I need x minus 1 to the bottom. That creates the LCD I was looking for, but then I have to balance with an x minus 1 to the top. And then I've got the parentheses that unfortunately I have to put in. This is very similar to what we did a minute ago. The only difference is I actually have more things needing parentheses around them this time. But that's what the step looks like, and I'm going to put here in the notes that those two factors, once again, can be switched around. So what I'm dealing with at this point, it looks like x plus 1 times x minus 1, and then x plus 1 times x all over the green LCD. Okay. Now, this is why I'm not sure where the wisdom was in just throwing this problem straight into the homework and not demonstrating anything like it in the bulk of the chapter, because this problem is messy. Once you get to the LCD step, you can kind of see that the expressions in the black here at some stage in this journey we're on are going to have to address how messy that is. That's not anywhere near being simplified. It's great that you have some factored pieces, but the fact that you've got pieces that are left out of the factoring means that really you're going to have to destroy all the factoring and like start over. And you'll see what I mean in a minute. I think what I'll do here, because I see some potential for canceling, we can go ahead and do the invert and multiply thing at this point. Because just the way they've set this up, so this is the very top expression over its little orange common denominator there. Okay, and then we can multiply by the inverted this fraction, this ugly fraction that we have on the bottom. We can flip upside down. So the green denominator is now the green numerator. And then all the rest of this junk just carries along. Okay. The reason I did that at this point, it's not a bad thing to do at any point really, but in this problem, notice that the green and the orange can cross cancel, even though this and this needs work before we're allowed to cancel. And similarly down here, I'll just write needs work. But this and that, those can cross cancel. The benefit of having identical little common denominators is that the green little denominator eventually became a numerator and canceled out with the other one. So As always, putting in as many steps as I possibly can here. What I end up with is the two things that need work. So it's like I've been able to get rid of everything else, but these two things need work. Before I can consider this problem done, I have to deal with these sets of parentheses. I have to distribute out anything I can and look for like terms. This is turning into kind of the end of a problem from 7.2, what we were doing last time and what we were kind of doing before the break. So if I very carefully distribute out, and I don't think I've run out of colors yet, if I very carefully distribute this out, I can get x squared minus x plus 2x minus 2, and then in the black, the minus 2x that was already a part of the numerator, but was not a part of the parentheses and jump. And then similarly underneath here, here in the pink, I'm going to choose pink. I can get x squared minus x plus x minus 1, I think. What's a good color that I haven't yet used? I'm not crazy about yellow, but let's see how that, I can actually distribute this x back into that x plus 1. Okay, so something like that. So everything in colors there resulted from me having to simplify stuff. The negative 2x is just hanging out, hoping that there's like terms coming along. So if I clean up the blue section here, I've got negative x plus 2x, so it looks like they'll come together as plus x minus 2. And then, so notice I'm cleaning up within the colors. I'm cleaning up the colors separately, and then I'll start looking across and see if there's anything else that can combine. These two, that just equals 0, so it's gone. And then really, plus x squared plus x, nothing happens there. Okay, at this stage, I think I'm about ready to be done with colors because I want to look at the numerator as a whole, the denominator as a whole, and I want to see, are there any lingering like terms? So what used to be the blue x squared here, it's all by itself, no like terms. But there are a couple of x to the firsts. So they're going to come together as a negative 1x. And then a minus 2. And then on the bottom, I've got a couple of x squareds. I've got only 1x. And I've got only one number. It's just a negative 1. Okay, we might be done with the problem at this point, but we also might not. And the only way to tell, just like where we ended in 7.2, we've got to factor and cancel. So I'm going to say this might be final answer. And that's one of the aggravating things about these problems. You don't really know when you're done sometimes. This might be the final answer. We have to at least try to reduce the fraction. And factor cancel is just the algebra way of saying reducing the fraction. So I'm going to put both of those in the notes. Okay, so we have to at least try that. Now, the top fraction, the top polynomial looks, because it has that 1x squared, it looks like one of those nice shortcut factorings. If it's going to work, we can just put x, and all we'll have to do is attempt to factor this -2 in such a way that the factors add to be -1. And thankfully, -2 plus 1, there aren't a lot of options when the numbers are that small. So pretty quickly, even having to play with negatives and positives, we can see that -2 times 1 gives us by multiplication the -2, and the -2 plus 1 by addition gives us that -1. So the top factors, that's good news because maybe they're going to lead us into a little bit of canceling. The bottom, this is one of those cases when you are not, unfortunately, starting with, wow, I switched to a marker, didn't I? When you are not starting with, where is that? A 1x squared, you're starting with an anything else in the world x squared, you do the AC method. So 2 times -1 is -2. You try to factor -2 in such a way that the factors would add to be that +1 that we have in the middle. Works out pretty well. Then you dive into the rewriting step where you leave the first piece alone, you leave the last piece alone, but you expand the middle piece. So instead of just 1x, now it's -x plus 2x, because those would add back if we were checking. We're kind of checking our steps here. Okay, so pulling out an x, pulling out, nothing comes out of this other 2x minus 1 except 1 itself. This is the time where, even though 1 is usually considered an unimportant greatest common factor, here it's a super important greatest common factor since we're in the middle of factor by grouping. So at that point, if you kind of trek over here with your factor denominator, bad news is, just because the numerator factor doesn't mean the denominator will factor. Just because they both factor doesn't mean anything will cancel. Here we're really lucky because not only do they both factor, but they do both cancel as well. We can cancel out, reduce by canceling out our x plus 1s. And then 2x minus 1. So that, and as I mentioned on Tuesday, sadly, if you have a problem that reduces and you don't reduce it, it's considered to be not completely correct. So even though you might have done all of this really complex algebra very, very well, and you get to this point, and this point is correct, it will not be accepted as the final answer, and it won't match what you see in the back of the book because they're going to expect this little tiny thing down here. So to me, that is one of the worst parts of this particular section of algebra, is that the stuff you're learning requires enough thought in and of itself. And once you get past the method you actually learned, there's always this cleaning up, and sometimes the cleaning up is worse than, or at least as bad as, what came before it. So it's just, I think that's one of the things about algebra that people just object to the most, is it's picky about the way it wants you to leave problems. But the secret is really, it's no more picky than regular old arithmetic. We've always been taught to reduce our fractions. It's just that reducing fractions back in the day was a minor inconvenience. Reducing fractions now is like a major exercise in algebra. So I think, yeah, I really can't, I'm not putting homework up quite yet because we're still sort of assessing where we're going to go from here. But I am going to work one more problem from the homework section, because when you and the Chappells get there, this is sort of a classic problem that we can't leave this section without looking at something like number 31. So here I've got just big picture. It's nice to take a few minutes and just kind of figure out overall, what am I looking at? I have a single fraction up top. I have two separate things below, and I can go ahead, since we've talked about this, just remind us that both of the things down under here are fractions in and of themselves. The one up top, I don't need to worry about an LCD or trying to add things together because they've been kind to me, given me this is already one fraction. So I can say this is already a single fraction. So it's already in the form that it needs to be for me to like invert and multiply eventually. Okay, so that's good. What are we going to do about this? Okay, so it looks like this needs an LCD, needs a, what I've just been calling a common denominator. And then the two pieces need to be added together. Now, between, if I stick with my method there of putting parentheses, it looks like between 1 and x minus 2, the only significant part of that is going to be x minus 2. So the denominator that I need to create actually is x minus 2, which means I'm going to condense things a little bit here just for time's sake. I can go ahead and fix the fraction that doesn't have the x minus 2. Okay. And then it looks like I've got, what have I got here? Something like this. When I add those things together, because now that I've got common denominators x minus 2, I can add the tops, and the tops are just x minus 2 plus 1. So I'm almost, but not quite, at the stage where I can invert and multiply. So x minus 2 plus 1, really the parentheses there at some point become unnecessary because I'm no longer multiplying anything. So if I just think of that as x minus 2 plus 1, that's just going to reduce to x minus 1. The parentheses, maybe at this point in the problem, it's kind of up to you. Get rid of that. It's never wrong to have them. You're welcome at this stage in the problem where you're thinking about inverting and multiplying, you're welcome to kind of take a pause on that and then worry about parentheses only if we need them later, which we will. Inverting and multiplying means that the top fraction stays the same. It simply gets multiplied now by the reciprocal, the upside down version of this. Okay, I'm very quickly going to, this is where my parentheses become important again, because otherwise I'll be tempted to start canceling out like individual x's when I'm not really allowed to do that. You can see right away that this x minus 1 can cancel with that x minus 1. But there's a tricky part in this problem, and honestly, I could have dealt with it way earlier than I did deal with it, but I wanted us to just kind of go through a streamlined process there. X squared minus 4 is not factored. So this is a case where it's like you get to this part, well, this could be the answer, but I know already it's not because this is not factored. And that didn't bother us earlier in the problem. We had no need for it to be factored, but at some point that is going to bother us, and this is that point. So in essence, the very instant that you noticed that was not factored, it could have been the very first part of the problem, you're welcome to go ahead and factor it. I saved it for the bitter end, and that, you know, could have been a good call or a bad call on my part. It's in algebra, I almost get to the point of thinking there is no such thing as a good call or a bad call. It's all just relative to what we prefer as individuals, and so sometimes you just have to roll the dice and hope for the best. So at the very least, the last step in this problem is going to require us to factor, just like the last step in the previous problem required us to factor. And we get left with this. Okay, that's where I would leave it. There are more of these homework problems I could do, but that pretty much covers, that's what the essence of what we need out of 7.3. Looking ahead to 7.4 and even 7.5, yeah, I'm just going to be pulling the bare minimum of what we need. For some reason, as the book goes on, there's more and more of these times where they show you multiple ways of doing one thing, and that's great, but it can be a little bit counterproductive. It can feel like reinventing the wheel, and it can get really confusing. So I'm going to stop there. I got an email from Max, like he was trying to log in, couldn't log in, so I'm going to go ahead and try and get the recording finalized so that he can listen to that. And then I guess your mom and I will talk about what we do next week if we meet in person. You know, Lord willing, everybody's healthy. Matthew is over whatever is going on, and that should work fine. But we'll talk about that and just see where we go from there. So let me go ahead and stop the recording and see if I can get this to where the chapels can see it. So hopefully I will see you guys on Sunday, if nothing else.
Thank you, ma'am, for class.
Welcome.
Thanks. Bye.
Bye, Matthew. Hope you feel better.
Okay, you can press the red. Let me save. I remember how I always record notes. This is 1-7. Okay. Let's try this. Can you hit this button, enter, now that I have it all lined up? Let's try that. Oops. Hit it. Hit it again. Well, that was a good thought. I was experimenting. Do what you did last time. Just hit here. Yeah, hit hard. This one time when it's, whoops. Well, you don't want to move it to the left or right at all. Just hit straight down. Just press right where my finger is. Oop, here, I'll show you. Boop, and then, whoops, nope, nope, nope. See that? And I messed it up. Okay. Oh, I don't even know what it's doing right now. I thought enter would work.